Hi. So we've come a long way since that single cycle data path. We introduced pipelining with in-order execution, and of course, in the last module, we explored out-of-order execution to increase the utilization of the functional units and of the pipeline with the broader goal of improving performance by increasing instruction throughput. But I ended on a bit of a down note. It turns out that Thomas-Wheeler's algorithm, while it increases performance, we had no clear plan for how we would handle exceptions or even control speculation or any kind of speculative execution. So that naturally brings us to the topic of this module. We will improve upon dynamic scheduling by adding support for precise state and speculation. The textbook content for this module will be the rest of chapter 3.4. So a quick recap of where we were. In the last module, we saw dynamic scheduling, also known as out-of-order execution, where we dispatched instructions in order. So this should say dispatch. But we issued instructions to execute as soon as their input operands were ready. We saw the abstract concept of an instruction window or instruction buffer, which enables us to examine a large number of instructions. And so hardware, the processor hardware, conceptually uses this instruction window to try to find independent instructions that it can then run out of order while respecting read after write data dependencies. The Thomas-Wheeler algorithm uses copy-based register renaming to eliminate write after read and write after write dependencies. Turning to this module, to enable control speculation and precise state for exception handling, we are going to rethink register renaming to a degree. So we are going to use true register renaming this time in contrast to copy-based, and you'll see what that means soon. And we will support these new features with what's called a reorder buffer, a key concept for this module. We're combining these ideas into an implementation, into a design called the MIPS R10K. So our goal is to understand the mechanics of how that processor achieved functionally correct out-of-order execution. As with the last module, in this video, we'll start with the motivation. We're going to cover all the problems that we're facing and that we expect to solve in the rest of the module. We'll see the high-level conceptual ideas, and then we'll dive into a microarchitectural implementation and several examples of how the structures are used in that implementation. So let's get motivating. Speculation and precise interrupts. Now you might be wondering, why are we discussing these topics together, motivating an entire module? Well, let's start by looking at the interrupt side of things, and maybe it will become clear why these are related. Starting from first principles, what are the sequential semantics, the von Neumann semantics for interrupts? Remember, this is that abstract machine model where one instruction is processed completely from fetch to register write back atomically before the next instruction even begins all of this processing. The sequential semantics for interrupts are that all instructions before some interrupt or exception should complete. The state of the memory and architectural registers should represent the completion of all of those instructions before the interrupt. And all instructions after the interrupt or the accepting instruction should look as if they never started. So why are we discussing speculation here as well? Well, we basically want the same thing for a mispredicted branch. So all of the instructions before a branch should complete, and all of the instructions after the mispredicted branch should look as if they never started, and then we continue the execution from the branch once we know the correct target PC following the branch. We want the same thing for interrupts and speculation. What makes precise interrupts difficult? We saw this in the last module at the very end, that down note that I ended on. It's that out-of-order completion. The out-of-order write back meant that some younger instructions wrote back before the interrupt or the exception. So we need a way to undo the post-interrupt writebacks. That's ultimately the one thing that went wrong in the last module. And interestingly, this challenge is the same for branches, for control speculation. In module 3, we saw that for an in-order pipeline, branches, in fact, complete. We know they resolve, we know their target before any of the younger instructions write back. So we simply squashed the younger instructions in the fetch and decode stage. But with out-of-order completion, this was not necessarily the case. So precise interrupts and control misspeculation, they both need recovery. They both have the same problem. We can even view interrupts and exceptions as a form of speculation. for any given instruction going through the pipeline, we're making a guess that it won't trigger an exception or that an interrupt won't come in to interrupt its execution. We have a means to detect when that guess is wrong, to detect a exception misspeculation, which is we can detect a divide by zero exception in the functional unit or a page fault in the data caches, etc. But in the Tomasulo design, what went wrong for both precise interrupts and control speculation is that we had no recovery mechanism, the third key component of any speculation. So since interrupts and control speculation have the same problem, well, we're going to see that they actually share the same solution too. Our solution is to retain precise state. So as I just said, speculation has three parts: a guess, a means to detect that the guess is wrong, and critically, the ability to abort and restart. So to recover. So in the case of control speculation, that is at every branch. Now what about precise synchronous or program internal interrupts, also called exceptions? Well, they require the ability to abort and restart at every load or store for page faults or permission exceptions, maybe integer or floating point divide instructions, trap instructions to invoke kernel code, etc. So you can imagine all of the sets of instruction types that might cause exceptions. To achieve precise asynchronous or external interrupts, this requires that we have an ability to abort and restart at every instruction period, as an asynchronous interrupt, by definition, could come at any point in the instruction stream. So we can see a lot of commonality between control, speculation, exceptions, interrupts, and so let's bite the bullet. Let's implement abort and restart, this feature that we seem to need, at every instruction. And we call this feature precise state. So what exactly went wrong in the last module? What was our problem with implementing precise state? So here's our conceptual view of a processor with out-of-order execution. This was shown at the beginning of Module 4, where the processor dispatches instructions in order into this abstract instruction buffer, which issues instructions out of order down the rest of the pipeline. Now the problem with that design was that the write-back stage of the pipeline combines two separate functions. First, it forwards values to younger instructions to ensure that we still respect read after write dependencies, and this was fine. It was okay for this to be out of order. We still respected the read after write dependencies. But the second function was to write values to the registers. And this is the feature that we would like to be in order. This second function is what prevented us from implementing precise state. Now, we saw a similar problem for out-of-order execution in the decode stage of our in-order pipeline. What was the solution there? Well, we split decode into two stages: an in-order dispatch, so the D stage above, and an out-of-order issue stage, so S above. And we separated the two stages using that conceptual, that abstract instruction buffer, which was implemented in the Tomasulo algorithm as reservation stations. So we saw a similar problem before and solved it by separating into two stages, one in order, one out of order, using some on-chip storage to buffer intermediate results. You can expect to see the same very soon in the next video. So wrapping up this video, I just want to revisit that problem we saw at the end of Module 4, where our store instruction here has a page fault, which we handle in cycle 18 at writeback, but unfortunately, 4 younger instructions also wrote back their results to the register file in the meantime. By cycle 18 at the writeback of the store, this is when we finally handle the exception in software, but we've lost our ability to recover the state of registers F0 and F4 and R1. They've been overwritten by these younger instructions due to the out-of-order writeback. Did this implement precise interrupts? Well, you can guess not. So our goal is for the state of the machine to look as if no instruction beyond the faulting instruction had issue, be it an exception, an external interrupt, control misspeculation, or other forms of misspeculation And we saw last module that Tomasulo had in-order dispatch, out-of-order execution, and out-of-order completion, or write back. And so we need to fix that out-of-order completion aspect so that we can find a precise exception point and restore the state of the processor back to that point. So I'll end this video here. In the next video, we'll cover the concepts of our solution, which is called a reorder buffer. So I'll see you there.